Today we're going to look at how to write a chemical's name from its formula. I have several different samples of chemicals here with me today. We're going to take a look at them. I'm going to give you the formula and we will walk through the flowchart trying to identify the chemical's name. The flowchart is posted in Schoology, so please make sure you have it up with you as we are walking through this video, walking through the names, so you can get some practice in how to use it. If you're not sure what the flowchart looks like, an image of it is posted on the screen here. The first chemical we're going to take a look at is a yellow crystalline substance. It has the chemical formula S8. This chemical has the formula S8. When we look at our flowchart, the first thing we notice is a question asking how many different kinds of atoms there are. In the chemical formula S8, the only type of atom we have is S. So we only have one type of atom in our chemical formula. When we follow that branch, it tells us that our chemical is named the same as the element. So this yellow powder or crystal, depending on the size of it, formula S8, we name it the same as the chemical element. The element name for S is sulfur. So when I look at the label on the jar, I see that this is the chemical sulfur. The next chemical we're going to take a look at is a blue crystal, and the chemical formula for this is CuSO4. This chemical's formula is CuSO4. The first thing I notice on the flowchart is a question asking me how many different kinds of atoms are there. In this chemical, I have Cu, I have S, and I have O. So I have 3 different kinds of atoms. So because I have 3 different types of atoms, I now follow that path. And the next question it asks is there a polyatomic ion in the formula? Looking at the formula, I see a group of elements that I recognize as a polyatomic ion. I see SO4. But on my polyatomic ion list, that's charged with a 2 negative charge. So do I count that? Do I not count that? As it turns out, in compounds, all of the charges get balanced out. So when we are looking at compounds, you won't see the charges on the polyatomic ions, but that SO4 group is still a sulfate group. So in this compound there is a polyatomic ion present. The next question asks, do I have a polyatomic cation? The only polyatomic ion I've recognized is sulfate, which is an anion because it's negatively charged. Since I don't have a polyatomic cation, I follow the path for no. Then it asks me if I have an S block, aluminum, gallium, silver, or zinc for the metal. I don't have any of those. So I follow the path for no. And then it tells me to name my cation. Cu is copper. Simple enough. And then it asks for the oxidation state of copper. So here we have to think back to the video on oxidation states. I know that in sulfate, all of the oxidation states have to add up to 2 negative. Because remember, one of the rules is that all of the oxidation states add up to the charge. So if I look at sulfate as a whole, it's 2 negative. So all of those oxidation states have to add up to 2 negative. Well, what does it take to balance out 2 negatives? 2 positives. So the 2 positives fall onto the single copper ion. So I have copper with 2 positive oxidation states, so I use the Roman numeral for 2, so copper 2, and then I name my anion, which is sulfate. So this is the chemical copper 2 sulfate. The next chemical we have is one that's actually dissolved in water. Its chemical formula is NiSO4, and you'll notice the last couple chemicals have had different colors. A lot of the transition metals have very vibrant colors in their compounds. Nickel tends to make green compounds, whereas copper in the previous compound tends to make blue colored compounds. Again, this compound's formula is NiSO4. I have three different kinds of atoms. I have nickel, I have sulfur, and I have oxygen. And again, I recognize that sulfate ion, so there is a polyatomic ion in it. But my polyatomic ion isn't a cation again. So I have to follow the branch where it's not a cation. And nickel is not an S block, it's not aluminum, it's not gallium, it's not silver, and it's not zinc. So when I name it, I still have to use a Roman numeral. Since the charge on sulfate is 2 negative, all of those oxidation states have to add up to 2 negative, which means the oxidation state on nickel has to balance it. So nickel, like copper, had to be 2 positive. So this chemical would be nickel 2 sulfate. The next chemical we're going to look at is a colorless crystal with the formula AlCl3. Again, this chemical's formula is AlCl3. Looking at the formula, there are 2 different kinds of atoms. I have aluminum atoms and I have chloride ions. So I have a colorless compound with 2 different kinds of atoms. I follow that branch, and the next question asks me, do I have a metal in the compound? In this case, I have aluminum, which is to the left of the stair-stepped line, so I do have a metal. So we're going to treat it like it's an ionic bond, even if it might not be a true ionic. This one is ionic, both in chemical formula and in experimental testing. So we're going to treat it like it's ionic. First thing I do is ask whether my metal, is it an S block metal? Is it aluminum, gallium, silver, or zinc? In this case, it is aluminum, so I follow the path for yes. And it tells me to name my cation. Remember, cation, when we write our formulas, is always listed first. So aluminum is my cation. I then name my anion and change the ending to IDE. Chlorine is my anion, so I change the ending of the atom to make it an ion, to IDE, IDE. And we're going to use the highly scientific method of which one sounds less dumb. So it'll generally follow a consonant. So you're going to sound like a maniac when you're doing this, but try saying them out loud and see which one sounds the best. So is it chlorinide, chloride, or clyde? I don't know about you, but chloride sounds an awful lot better than chlorinide and clyde. So this chemical is aluminum chloride. Next up, we have another chemical dissolved in water. This one is NH4OH. This chemical in a diluted form you might find in your house. When dissolved in water, ammonia turns into this chemical. As I was saying, this is a chemical that you can find in your house. When ammonia is dissolved in water, this is the chemical that you get. It has a very distinctive odor. I'm sure all of you recognize it. It smells like ammonia. Looking at my formula, NH4OH, I have 3 different kinds of atoms. But for some reason, they represented H twice. Why might they have done that? Well, in this case, it's a little bit of a structural formula. It tells us a little bit about how things are bonded together. So I follow the path for 3 or more, and then it asks, is there a polyatomic ion? Again, we won't see the charges, but they are there. I recognize the NH4, that's ammonium, and I recognize OH, which is hydroxide. Ammonium has a positive charge, hydroxide has a negative charge. So because ammonium is positively charged, it's a cation. So I do have a polyatomic cation. When I follow that path, it tells me to name the cation, which is ammonium, and then name the anion, which is hydroxide. So this is ammonium hydroxide. Next chemical we're going to look at is a colorless crystal. Has the chemical formula C6H12O6. This chemical might throw you a bit of a curveball as we're walking through the flowchart, so make sure you follow along as we're going. So remember, we need to be paying attention in this. This one might be a little tricky. This one is C6H12O6. And you might be thinking to yourself, I know that one. We were taught that in biology. C6H12O6 is glucose. Well, let's take a look and see what we can come up with. I have 3 separate kinds of atoms. And I don't see a polyatomic ion in that formula, though. There's some that look similar, you know, like acetate, or maybe I could make a hydroxide, but they're not shown together. So this is a case where there's not a polyatomic ion present. So if I have 3 or more atoms, no polyatomic ion, how do I name this? Well, for our purposes, I don't know. This is a chemical that we don't have the tools to name yet. For large or complex molecules or organic molecules, carbon containing, they follow their own set of rules for naming. And sugars like this one, which is actually levulose instead of glucose, which is a derivative of fructose, or a type of fructose, I should say. Sugars and organic molecules have their own set of naming rules. And we'll cut away and I'm going to show you why, even though they have the same formula, they have different names. Let me give you a brief demonstration why our chemical that was C6H12O6 isn't glucose. So I have here a ball and stick model of levulose. Levulose is a specific type of fructose. Fructose is the type of sugar that you typically find in fruit. So it's a slightly different sugar than what glucose is. And here I have a ball and stick model of glucose. Let's take a closer look at levulose and glucose. So here we have a bit of a closer look at levulose. And you'll see a ring of 5 atoms. The black ones represent carbon, the red ones represent oxygen, and the white ones represent hydrogen. So in levulose, we have a ring of 5 and 2 carbons attached to the ring on opposite sides of the oxygen. And the way these are attached make it either levulose or another form of fructose, L-fructose. So here we have a model of glucose. In glucose, rather than having a ring of 5 atoms, we have a ring of 6 atoms. We only have 1 extra carbon to attach to our chain. And the oxygens get attached in different ways depending on what type of glucose we have. Tells us which direction the oxygens will point off of it. So hopefully this illustrates to you that when we get a little more complex compounds, the formula isn't all that matters. How it's attached together changes what the chemical acts like, what it behaves like, and what we would call it. We're going to look at just a couple more examples together. I don't have samples of them in the stockroom, but I can make a sample pretty quickly. So in this balloon there are several different elements. There are different compounds, there are different gases. A lot of what was in the air makes it into this balloon. So N2 is the primary component of air. Our bodies don't process it when we breathe. So any of it we breathe in, we just breathe right back out. N2, if we follow the pattern, 1 type of element, named the same as its element. So we have nitrogen. N2 is nitrogen. We also have O2. Our bodies don't process all of the O2 that we breathe in, only a portion of it. Again, same as the element. What our bodies do process of the O2, we breathe out as CO2. So if we follow our patterns, we have two types of atoms. We don't have a metal, so I use a prefix for the first atom, C, just one C. So I use mono, but I don't have to use mono in the first one. So then I name the first atom, carbon. Prefix for the second atom, O2, so I'd have two oxygens. So the prefix would be di. And then we've used oxygen a little bit already. So this would be oxide, so carbon dioxide. So our bodies process the oxygen we take in and give it off as carbon dioxide. It just seems cruel to me to keep all of these atoms and compounds and elements trapped in such a small space. So let's let them out.